Assalamu alaikum everybody. Today we will start about session 10, data of TM351, data management and analysis, and start with part 19, which is about data warehousing. So what is data warehousing? Data warehouse is a repository of operational data organized around the subject of interest, such as customer, products, location, sales, and many others. So all these feature data stored in data warehouse. The data could be collected from different or multiple sources. We use this data in decision support system, which we mentioned about it previously, which is a computer-based system that incorporate data warehouses and employ data mining to facilitate and improve strategic decision making. And we also mentioned about data mining before that. So we have to prepare the data warehouse, make the data ready for use by the application, for example, and then we can apply the DSS and data mining algorithms on the data warehouse itself. Uh, as an example, we may mention, for example, the science of a climate change, and then we have to look at the following: the subject oriented, which means fits with the data, with the research needs. Okay, then integrated data set is typically derived from several independent institution organization. So as we mentioned, then the time variance, then non-volatile, so the data is not changed. The data warehouse itself is a kind of historical data. Every time we add to the data warehouse, okay, we don't overwrite, but we add. So finally, the data will be historical data for long period of time during different time periods. The architecture of a data warehouse consists of four different components. The information sources, where we will get data from, and then the core component, which is the ETL, starting with the extract process. We extract data from the resource, then transform the data to a suitable format, then to load the new transformed data to the data warehouse. And then the enterprise data warehouse component and the business intelligence applications, which will use the data in this enterprise data warehouse after the process of transforming the data collected from different sources. Two important aspects of ETL system: data cleaning and data integration. We talked about data cleaning before. So we need to find the errors, and then to overcome these errors. Errors could be incomplete data. We call it missing data before. Noisy, inconsistent data. So all these kind of errors that may appear in a data. So we need to go for two steps: to the data analysis to detect the errors, and then data transformation rules, which use specific rules to overcome or clean the errors detected. Data integration has two main aspects. format integration and semantic integration. Format integration, because we are collecting data from different resources, so the format could be different from for the same attribute. It is impossible to integrate uh, the same two features from two different resources if they have different format. So we should transform the format one to another, and then we can integrate them together in one new attribute, for example. Example, some maybe date collected from source A using the format day, month, year, and the other feature from source B used year, month, day. The format is different, so we need to do the format integration process in order to have the same format for the new attribute loaded to the data warehouse. This is another example. If we talk about salary, maybe take salary from source A, which is using US dollar, and the salary from source B, which is using Kuwait dinar. So they are different in format, in the format, their format, and we need to conduct the format integration process also for this case. These rules that are used for format integration process will be stored or saved in the metadata repository of this data warehouse. About semantic integration, meaning of data can be different depending definitely on the view of the data from different departments in an organization. Semantic integration concerns ensuring consistent meaning of data extracted from different operational systems. Okay, data in data warehouse could be aggregated uh, basically based on the need of the user. So it could be aggregated yearly, quarterly, monthly, weekly, daily, or whatever. For example, we say we want to find the sales of the company, our company or X company, the yearly sales or the weekly sales or the monthly sales. So we do this kind of aggregation based on the needs. The aggregation chosen to be pre-computed referred to as materialized views depend on the decision maker's requirements. So remember that this aggregation called materialized views. In order to exploit effectively the use of materialized views, the following issues need to be addressed. View selection. Okay, so which views or aggregates should be materialized or pre-computed and stored? Then view maintenance. Okay, it's talking about warehouse database updates. If this update happened to the data warehouse, then how we will maintain such thing. And then the view use, which views are available to satisfy the request. So we have view selection, view maintenance, and view use. Okay, the structure of multidimensional data models. We will see now that we have one-dimensional data model, two-dimensional data model, three-dimensional data models, and could be more. This is an example of one-dimensional data model between product and sales. So you can see the product, for example, the milk product and the sales of such product, which is 30 million. Juice product and it sells 24 millions, and so forth. So this is a one-dimensional view of sales. Go further to take another one-dimensional view between store, location, and sales. So for also this example, we can look at the store location, London, for example. Sales in London location is 39 millions. Sales in New York City is 23 millions, and so forth. So if we want to combine these two one-dimensional views together, we will get two-dimensional view, which holds which will hold product, store location, and sales. So we will get this two-dimensional view. Okay, you can see here clearly. Okay, for example, take the first product, milk product. Okay, sales of milk in London is 10 million. Sales of milk in New York is 5 million, and so forth. Also, you take it as milk, this product sold in London by 10 million, juice 8 million, ham 12 million, jam 9 million. Okay, if you count, if you sum them all, so you will get 10 plus 8 plus 12 plus 9, which is 39. Okay, so this 39 means sales of all items in London. So 39. If we go back, so we can get here for London, sales is 39 millions. Okay. We may consider time as the third dimension and include it in our view like this. Okay, for example, milk product in London. Okay, but I want to show you this. Okay, this is milk. Okay, sold in London. Okay, we have some problem in the alignment here. Okay, this milk for alignment for London. Okay, in the first quarter, and then we will have milk. Okay, in London. This one is in London. Okay, in quarter 2. This is the time. We can go further and also take milk in London for the third quarter of the year and milk sold in London in the fourth quarter of the year. Okay, so if you count them, you'll find that the sales of milk during the year in location London is 10 million as we saw previously. So you count 3 plus 2, and then if we go further, So 3 plus 2, then okay, 5, and then you will take uh, 3. Now it is 8, and the last one is 2, then we have 10 millions. Okay. Views of multidimensional data. For any n-dimensional space, we have 2 to power n different views. If we say that, for example, we have two-dimensional views of cells, then we will have 2 to power 2. Then we will have 4 different views. Okay. So for the two-dimensional, we will have 4 different views. What are they? It is, okay, remember, when we talk about the two-dimensional, I said that we combine the first two one-dimensional views together in two-dimensional view. So we will have one-dimensional view, the first one-dimensional view, the second one, then two-dimensional views, combine them together, and one empty view. Okay. For example, we have product and location. So we have view for a product, view for location, view for product and location, and then one empty view. Let's say we have 3 dimensional views: product, location, and time. Then how many different views we will have? It will be 2 to power 3. Then how much? 2 to power 3? 8. Okay. So what are these 8? It is product, the first view, then location, then time, then product, location, product, time, location, time, what else? Then we will have a product, location, time, and one empty. Okay. Data cubes, because the data can be generalized to a grid with any number of dimensions, modeling the data in this way is often referred to as dimensional modeling, and the multidimensional grid is called data cube. We will see this. So data cube has different terminologies. Okay, cell, the combination of dimension values define the cell of the cube. Fact, a non-empty cell in the cube is called fact. Measures, measures are numerical values that are associated with facts. So we have cell, which is empty. We have fact, which is non-empty cell, and then we have the measure, the value inside the cell. A cube can have any number of dimensions. Hypercube is often used to refer to a cube that has more than 3 dimensions. For us, it is simple to notice, to understand the 3 dimension. You know, any cube is a 3 dimension XYZ, but if it has more than 3 dimensions, then it will be called hypercube. In cases where there are a number of cubes that are related to each other, we have cube 1, cube 2, cube 3 for the same data warehouse. then this collection of related cubes is commonly referred to as multidimensional database or multidimensional data warehouse. Types of measures, the values inside the cells. So we may have any of the following. The first one is additive measure values can be meaningfully combined along any dimension, such as total sales that can be meaningfully summed over any of the dimensions, product, location, and time. If we can use all the dimensions, then it is additive measure values. Semi-additive measure values cannot be combined along arbitrary dimensions. For example, if you talk about the inventory levels, we cannot be summed across time, but they are summed across product and location. We can find the product, the inventory for the location or the inventory for the specific product, but not for the time dimension. And non-additive measure values cannot be combined along any dimension, and this has happened if we talk about derived values such as average, standard deviation, or whatever. So if it is derived, then definitely we cannot use them for any kind of measure. Operations on multidimensional data models include OLAB operations. Also, we mentioned about this before, but we are going to talk some details about this. The commonly OLAB operations are roll-up, increasing the level of aggregation, drill down, decreasing the level of aggregation, slice and dice, it is the selection and the projection process, and then the pivot, or reorienting the multidimensional view of data. We are going to talk in some details about the first three operations. Okay. Slice and dice perform selection on a data cube, resizing the size of the cube. Oh, no. Slice, take a slice, okay? So we may take the first slice or first cover, the second slice, the third slice of the cube. This is the process of slicing. In this case, we will reduce the size of the cube. So if the cube consists of 10 slices, I take one slice or two slices, then definitely we reduce the size of the cube. And for dicing, we also minimize, we take number of slices, but not for all products, for example. We will see example right now as shown in figure 19.6 and 19.7. This is a slice. If it is a cube, then we have here 1, 2, 3, 4, 1, 2, 3, 4. So it is 4 by 4 cube. We take one slide of this 4 by 4 cube. You can see locations, time, then products on the other side, full of products, and then those are the three dimensions, and we call it the dimension. And then we have the values here. These are the measures. This is the cell. Okay. And of course, they are all facts because they have values, not empty cells. And this is the slicing. And if we go here, we can see the dicing. You see, for dicing, we only take uh, part of the locations and part of the products. Okay, we may take them for the whole timing or for even part of the timing, so it depends, but we don't take the whole cube for this process. Roll up. Okay. Roll up performs an aggregation. The result of the operation is to produce summary data from detailed data along one or more dimensions. Drill down aims to move to a more detailed view. So this is the difference. For, for roll up, we reduce the details. Drill down, we go for more details. We can see this. For rolling up, also, we reduce the number of dimensions, as we will see in these examples. Okay, we look at this example. Try to show the whole figure. Okay, look at the left side. So we will have this long view, which consists of time, you can see the location, and products with so many details. You can see the numbers there. So this is a 3D view, right? Because it consists of 3 dimensions, or uh, they are time, product, and location. So we can roll up this 3D view into the one shown on the right side, top right, which is one-dimensional view. So we reduce number of dimensions in this case. So this is the rolling up. We aggregate. Okay, يعني احنا دمجنا صغرنا. Okay, so this is the process of aggregation from 3 dimension to 1 dimension through the process of rolling up. What about this? It is rolling up. You can see that the first view has some details, but the second view has less details, so it is rolling up. For a drill down, we increase the number of dimensions. We will go for more details. So we may start with this example. We can see that we have this view. Okay, it is very aggregated view. It consists of location and sales on each location. Okay, for rolling down or drilling down a process, we get this view which consists of more details, and these details shown by time, quarter 1, quarter 2, and so forth, and then the location, different locations here. So we have the sales of each location for a specific period of time based on a quarter. A little more on OLAP systems. We want to mention some important notes also. There are two different approaches to implement OLAP systems. Uh, the first technology is relational OLAP called ROLAP, and the second one is multidimensional OLAP or MOLAP. ROLAP systems employ a relational database system to store the data as fact tables and dimension tables. So we take the data warehouse cube and convert it into tables, relational tables. As we can see in this example, we have this part of the cube, and we want to convert this part of the cube into relational tables. So we can see uh, that we have this table on the right, top right. Okay, you can see first we build product table, and in the cube or part of this cube, the dice, we have two products, ham and jam. So we use ham and jam and give ID for each one, like P1 and P2. And the same thing for location. How many locations we have here? We have London location, York location. So this is London and this is York location. Okay, and then the same thing for the timing, quarter, Q1 and Q2. Okay, and then we just use the data inside this cube, okay, inside the table as shown here. Okay, I'll show you some of them. For example, we have ham 3. Okay, this is the product. Okay, ham 3 is here, and okay, and then we have ham 4. This is for the second slice. Then we have 2, this 2 here, and then have 1, this 1. Then we have 2, this 2, and then we have 3, this 3, and then we have measure 1, which is here, and then we have measure 2, which is here. And we repeat the same thing or given the ID for each of these products or these values based on product location and quantity. MOLAB systems implement the multidimensional data model directly using a multidimensional database system. We give some advantages and disadvantages for each. For MOLAB, it is actually faster query response time and more space efficient storage. For relational OLAB, it is more flexible. It is better support for frequent updates. We can combine them together, MOLAB and ROLAB, as a hybrid OLAB system which is HO lab. Uh, HO lab system attempts to integrate the advantage of RO-Lab and MO-Lab systems, but at the cost of a more complex system architecture. This is the problem in that. This is all for this chapter's data about data warehousing, and uh, we will go after a while to study the next chapter, which is talking about data mining system. Thank you for listening and goodbye.